Today again I want to also just talk about this thing called propagator in quantum mechanics. So let me do that too. So what exactly is propagator? I really don't know. Whatever I see, I will talk about it. So suppose you have a wave function, some wave function. I will try to be as generalized as possible. And you can expand this wave function in some basis. Let's call them something like this. That's what we do, right? That's very trivial. Everybody does that. And I will say that uh, let's say that I know my state at some time t equals t naught, and at some time t equals t naught I know my state, which is this. uh, and now the thing is, I want to know how will this state evolve as time passes, given that I know what was the state at t equals to naught. So how would I do that? So it is just that I need to apply the unitary operator, the time evolution operator on the state, which will give me the time evolution of my state. And so if I do that, I will get something like this. That's what quantum mechanics says. That what the math formalism is about. I really don't have any deep why exactly. Like I don't have all the subtleties, but this is how we have the formalism, and if this is the case, and suppose I can expand this into its basis at that instant which I knew, which now I can write this as something like this. Uh, okay, let me use I. And so if I suppose that there are these are the bases, and each basis is a pure state having energy I, so this can further be decomposed into this. So this is my state at any instant of time t equals t naught. And now this here is my coefficient as a function of time of my wave function of my state. So what is next? So what is propagator uh, doing now? So you can see it is the same thing done in this book. I just try to make things according to my convenience, but more or less it is the same thing done in the this book and whatever I have written. And now the thing is, uh, so if I want to find out the value of this state, uh, like I want to find the probability amplitude of the state at some position x prime or x whatever. So basically what I mean is the amplitude probability amplitude of this state at x at some time t, given that it started at t naught, is equivalent to saying that it is it's I just take the inner product of the state. And now and now so and now so if I do this, I can just again do the algebra. To do this, and this can get inner product with this, and so this is what I would get. Oh, okay, so this I is not the same as this I, so I have to be careful. So I will just make the uh, dot of this I, imaginary I, very dark, so that it is not the index one, but it's something. It's just it's a imaginary, pure imaginary complex number. So oh no, not this one. Only this. These are different than the I index. So also, so that's it. So now if I do this, oopsie, again, I get this. This is my wave function at some instant of time for the position, and ability, given that I knew the initial condition at t equals to t0. And now this is index here. And now uh, also remember that these repeating indices just mean that I'm adding all of them over, so nothing more than that. And next, what is next here? Mm, more or less this is how we write the state. So what exactly is propagator here? So to understand the propagator, we have to think in terms of space, both continuous, we have a space, a continuum, and time of course, both space and time. And what is this exactly? So basically I have some functions. These are functions of x, and these functions of x, let me call them a of x, because why not? A of x is inner product of x with ai of x, of course. With a basis I, in the functional space, this is how I will write them. And this is nothing more but you know uh, I can also write them like this, uh, x prime of ai, summation over all the positions. This is corresponding to delta of x minus x prime, and ai of x prime times dx prime throughout the space of ai of x. I can write this like this as well. And why am I doing this? Even I don't know, I have to see. uh, he did that, he did everything. So hmm now uh, uh, so I can do this for any arbitrary x prime, doesn't matter. And not to forget that these ci's I actually get from taking inner product of the basis with my state at some time t naught. This is a constant I get. So in the more generalized form, I can write my state, I mean my wave amplitude, as this. And not to forget, this is getting summed over all the indices. And this is not an integer, this is just an imaginary number, a very confusing notation. Sorry for that, but these are two are the same. This is not same. Yep, and so this is imaginary number, not the I you're thinking. So now so if I can expand any wave function in this form, and why do I have an x double prime here? No x double primes, only single primes. Only single primes. So so far this is this a function in the functional space. This is this constant, and this is just this, and they are all getting summed out. And so what is this book telling? I don't understand. So if I can write for x prime like this, notice that for some other x prime, let's say for other x double prime, I can also write the same thing. T naught. This will be again the summation e power I by h cut e I minus e, I mean e I t minus t naught, and a I of phi of t naught and x double prime of ai. The only difference here is this, right? And so what I can do is I can I am free to write this in terms of my old basis x prime, I mean in this basis. So if I do that, for some reason if I decide to do that, I can write this as x double prime x prime uh, x prime ai, and I don't know what would I do with it. So, and this also looks very ugly. So I think I better not do that unless I know what I'm doing with it. And so then let me just have a look again. Mm, well, it is really hard. I mean, what can I say? It gets really hard, confusing, I would say. I don't know what I'm doing. It is difficult, but you have to do it. So one important thing I would say, uh, like suppose if you have something like this, uh, you are trying to do this. Uh, what was that? If you have this and you want to express this in terms of x, you can't just simply write something like this, even though it makes sense. Mathematically speaking, these x actually form a continuum. So this actually corresponds to an integral, which will be something like this. Basically, this is equivalent to integral of ai of x prime psi of x prime, and there is t is assumed tx. Oh, and this is q, by the way, all space. So this is how it is, and if I can write things like this, so this must be this. I don't know what would I do. Let me try writing the expression in its Fourierist form and then conclude what is happening. I thought I would be able to uh, get the essence of it, but I am not able to do that. Maybe skill issue, you can say. Uh, and what can I say? Let me just write this down and see what happens. So this can also be equivalently now written as summation over i's are confusing me, so I will from now on use j e power minus I by h dot e I e j t minus t naught. Now this will be my integral of ai of x prime, no, aj of x prime, aj of x prime phi of x prime t uh, dx prime cube, and it is aj of x double prime integral. This is integral over x prime. I would, to keep things simple, I will also omit this cube, just assume integral over x prime. And now Mm, by a little rearrangements here and there, you can actually write this thing. How can you write this thing? And actually, since this is getting integrated over x prime, uh, these are all just basically constant for x prime, and you can just represent all of this. You can pretend as if you are just integrating everything with respect to x prime, everything inside. Sigma is inside as well. I will just omit writing that, and summation is over j. A of x prime, I mean aj of x prime, aj of x double prime, aj of x prime, aj of x double prime, psi of x prime of t. And now, okay, finally we are good. Finally we are about to end this quantity here, which is getting summed over j. Nothing else is getting summed over j, right? So this quantity, which is getting summed over j, is the propagator of my wave function. I don't know what is so special about this, but that's what a propagator is. Kernel of the integration, fine. So they are claiming that the time dependence of the wave function can be predicted, can be well predicted by the propagator, the time evolution of our state. That's that's nice. And they are saying Schrodinger equation is a kind of should I say deterministic? Not exactly. I mean, given initial conditions, you will know exactly how the wave function will evolve. That's for sure. But you can't still for certainty say that what will be the result of your measurement. That's not allowed. You can just tell what are the possible probabilities as time passes. So we have some things here to be noted. Hmm. Hmm. So we have. So he's saying I can also write propagator as like this, which is also nice. Why do they give useful things afterwards? Propagator. I don't know how to write this. Maybe this is just I will just write it as this. X double prime x t given at t naught is equivalent to expectation value of x double prime e power minus I by h hat Hamiltonian t minus t naught with x. So I I will try to talk about Green's function next time. So that's all for now.